Hello. Now we have the next topic is analogous system. So first of all, the question arises, what exactly the analogous system is? So analogous systems are those systems, or we can say that two or more systems which are governed by same equation, or we can say that their differential or difference equation are of identical type, and it must be noted that the constants may or may not be identical. So in our syllabus, we have to develop the analogy in between the electrical system and mechanical system. Electrical system versus mechanical system. So now we can discuss these two systems one by one, and after discussing both these systems, we can interlink it and say it that those particular systems are analogous systems. Alright. So first we have the electrical system. So now we are discussing the electrical system. So broadly, if we say the electrical system, then electrical system is based on three elements. Number one, resistor. And if we consider the resistor, then if we say that the current along it, the resistance of R, the current along this particular resistor is IR, and the voltage in the resistor is VR, then we can say that VR should be equals to R into IR. Okay? And if we take this equation in the form of current, then it should be 1 upon R into VR. Alright? The second element is inductor. So if we take inductor, then in this case, similarly, now consider that the current along is IL with the inductance L, and the voltage difference between two terminals is VL. Then we can develop the VL as L into DIL upon dt. And IL should be equals to 1 upon L integration of minus infinite to t into VL dt. Here we take the integration from minus infinite to t because of having the property of energy storage in the inductor. An inductor is stored energy in the form of electromagnetic energy. So it can be written as 1 upon L 0 to t VL dt, and from minus infinite to t we can say it as this phi L0 minus. Here we consider phi L0 minus because phi, the current is, the energy stored in the inductor is in the form of current, and this This file indicates the electromagnetic flux which is stored in the previous session. Alright. Now we have the next. So here we develop the BL as well as the IL relation. Alright. Similarly, we can develop the relation in the capacitor. Our next element is capacitor. So similarly, in the capacitor, if we take the current across capacitor is IC and the voltage across it VC with the capacitance of C, then here IC should be equals to C dVC upon dt, whereas VC can be written as 1 upon C minus infinite to t into IC dt plus of, here we take the integration from minus infinite to t, or we can take the integration from 0 to t IC dt plus Q0 minus, because in case of capacitor the energy is stored in the form of charge, because capacitor is stored energy in the electrostatic field. So in this case we can consider, if we have the initial condition, then we can take the initial condition as charge, whereas initial condition in inductor we can consider it in the form of flux. Alright, so here we have the two equations, IC and VC. Okay, now we can take our next system, that is mechanical system. Alright. So in mechanical system is broadly categorized into two formats. That is, number one, translational system. And the next one is rotational system. In case of translational system, we can discuss the mechanical system in the form of forces, whereas in case of rotational system, we can discuss the mechanical system in the form of torques. Okay, so let us take it one by one. In mechanical system, for the translational system, we have basically the three elements. Number one is inertia system. So in inertia, if we have a mass of m, and here we apply a force with the displacement x and velocity v and acceleration a, then we can say it that F equals to inertia force equals to mass into acceleration, or we can say that it should be mass into acceleration can be written as dv upon dt. or in the form of displacement, we can write it as d2x upon dt square. Okay? So here we have the inertia force. Now, the second element will be damping. In damping system, if we have a damper connected across any mass, then if its displacement is x and velocity is v and acceleration is a, for damping coefficient capital D, then damping force Fd can be written as damping coefficient with velocity v, or we can write it as d into dx upon dt. Okay? So now, for the third system, that is a spring system. Spring, for spring. For spring force, we can write it as Fs if it is displaced by displacement x with the velocity v, then it can be write it as Fs equals to spring constant, that is k, into x, or it can be write it as k into minus infinite to t into v dt. Here we also take the integration form minus infinite to t, because the spring can also store energy in the form of displacement. So we can write it as k into 0 to t v dt plus x of 0 minus. Okay, so here we have the three translational forces, that is inertial force, damping force and spring force. Okay, so it will be similar for rotational system, but the difference will be where we write the forces like inertia forces, damping forces and spring forces, we can write it as torques in the case of rotational system. So now here we can change this translational system as rotational system. For the case of rotational system, here we can discuss the inertial torque. In the case of translational system, we can discuss the inertial force, whereas in the case of rotational system, the first element will be inertial torque. So in the case of inertial torque, a moment of inertia of I and with the angular acceleration alpha and angular velocity omega with angular displacement theta, we can write a torque. For torque, we can write it as torque. So Ti will be equals to I into alpha, or we can write it as I into d omega upon dt, or we can also write it as I into d2 theta upon dt square. Okay. For damping torque, damping torque. Here we have a damping system. If it moves as angular acceleration alpha, angular velocity omega, and angular displacement is theta with the damping coefficient d, then torque in case of damping torque will be equals to damping coefficient with angular velocity, like translational system. If in the case of damping force Fd, here we are writing it as d into v, whereas in the case of rotational system, in case of damping torque, we can write it as d into omega. The difference is only for v and omega. Here v is the linear velocity, whereas in the omega, in the case of rotational system, omega is angular velocity. Alright? So it can also be written as d into d theta upon dt. Now, for the third element, that is spring torque. The spring torque for angular acceleration alpha, angular velocity omega, and angular displacement theta for spring coefficient k, it can written it as Ts equals to k into theta, or it can also be written as k into integration from minus infinite to t into omega dt, or we can also write it as 0 to t into omega dt plus of theta 0 minus. Like we have already discussed in the case of translational system, in a spring case, spring force, the linear velocity is displaced with angular velocity, whereas linear displacement is displaced with angular displacement. Okay, so here we discuss both the system, electrical system and mechanical system. Now we are moving to develop the analogy in between these two systems. Okay. So before develop the analogy in between these two particular systems, we have to develop the governing equations. Before developing the analogy in between these two particular systems, in electrical system is governed by two principles. Number one, KVL, that is Kirchhoff voltage law, and number two is Kirchhoff current law. Okay, so in electrical system, in case of KVL, we can write the equation of all the three systems like inertia, damping and spring, and also in the case of KCL we can write all the terms in the form of current. Okay, here we write the equation in the form of voltage. So in the case of resistor, the KVL equation will be VR equals to R into IR. Whereas in the form of KCL, the IR will be written as 1 upon R into VR. In the case of inductor, we can write it as VL equals to L into DIL upon dt. Whereas The inductor current or IL is given by 1 upon L 0 to T into VL dt plus of phi of 0 minus. Okay. In case of capacitor, the capacitive voltage VC is given by 1 upon C minus infinite to T, or we can write it as 0 to T into IC dt plus of Q0 minus. And for KCL, we will be using the equation IC is given by C into dVC upon dt. Okay. So electrical system is governed by KVL and KCL. Now, in case of mechanical system is governed by D'Alembert principle. So the next question arises, what exactly the D'Alembert principle? So D'Alembert principle says that in a body, the external force applied on a particular body, that is M, will be equals to the summation of all the resisting forces. And in the case of resisting forces, we can use the term VFI, that is inertia force, FD, that is damping force, as well as Fs, that is spring force. Or we can draw the diagram it as, if we take the free body diagram, if we take FBD of this particular mass body, then F will be directly equals to the summation of all the resistive forces. These three are resistive forces. And F is called the external forces. So F should be equals to Fi plus Fd plus F of S. So in case of mechanical system, the mechanical system is governed by D'Alembert principle. For the mechanical system, we will be using the D'Alembert principle, and after applying the free body diagram, we can write it, the equation, in the form of forces, or it is for translational system. Or we can also write it as the external torque equals to inertia torque plus damping torque plus spring torque in the case of rotational system. Alright. So till now we are discussing the electrical system, the three elements of electrical system, and the three elements of mechanical system, for both the cases translational system and rotational system. Now we can develop the analogy in between the mechanical system as well as in the electrical system. So now we take the example of electrical system and develop the relation, and after taking the electrical system we can take the mechanical system, and then after we may develop the relation, or we can say the analogy in between the mechanical and electrical system. So now For a very basic electrical system, a series RLC circuit are connected across the voltage source V. Okay, so it will be R, L and C. The voltage across resistance is VR, across inductor is VL and across capacitor is VC. But it is the case of series circuit, so there is only one current, that is I will be flowed in the circuit. So in the case of series circuit, we can say that I should be equals to IR or IL equals to IC. Now we can apply here by applying KVL in the circuit. So V equals to VR plus VL plus VC. VR can be write it as R into IR and IR equals to I. So it can be write it as R into I plus VL can be written as L into DI upon DT. The IL is replaced by I here. And for capacitance, 1 upon C and 0 to T into I dt plus of Q of 0 minus. So it is the equation. This voltage is externally applied voltage in the series circuit. So this equation can be write it as equation number 1. So in the mechanical system, we can also take the example, the basic example, that is a single mass which is connected by a damper and a spring, and here we have applied a external force F on it. So after applying the forces, the force F, the acceleration of this particular mass will be A, the velocity will be V, and the displacement should be X, whereas the spring coefficient is A and damping coefficient is B. Okay, so now first of all, in the mechanical system, we can draw free body diagram. That is FBD of mass M. Free body diagram of mass M. So in the mass M, an externally force F applied on the right hand side, and because of a external force applied on right hand side, there will be 3 forces. The first one force is resisting from the inertia. So it can be write it as Fi. Here spring can resist the motion of the mass M. So here Fk, and also here damping force can also resist the motion of the mass M. So for D, here we write it as Fb. So by using for static equilibrium condition, the external force by applying the D'Alembert principle, the external force F should be equals to inertia force plus damping force plus spring force, and it can be write it as mass into acceleration, or here we can write all the three forces in the term of velocity. So Fi can be written as Fm into dv upon dt plus Fd can be written as d into v plus k can be Fk can be written as k integration from 0 to t into vdt plus of x0 minus, and it is the equation number 2. So now by taking the equation 1 and equation 2, we can draw the analogy in between the two systems. We can draw the analogy between two systems, that is electrical and mechanical system, and call this analogy as FV analogy, force voltage analogy. So in force voltage analogy, force is represented in the mechanical system, and velocity voltage analogy, voltage is represented for electrical system. Okay. So for external force F, here we have the mechanical system and we have the electrical system. So F is somewhere equals to V, because in the analogous system we already discussed that the constants may or may not be identical. So external force F should be equals to voltage, force voltage analogy. So F should be equals to V. Now, as compare the two terms, that is Ri and mdv, d into v, here, and this one term, this mdv upon dt, somewhere equals to ldi upon dt, because their differential equations are exactly identical and the constant may or may not be identical. So by considering these two terms, LDI upon dt and mdv upon dt, we can say that mass will be analogous for inductor, and also I, current, is somewhere equals to, we can write it as M for L and I is for velocity. This term is for velocity. Velocity is represented by current. Velocity is represented by current, and mass is analogous for inductor, as well as the damping coefficient D is analogous as R, and also spring force K is analogous to 1 upon C, and also for displacement in mechanical system is analogous for charge in the case of electrical system. So here we develop the analogy in between the electrical system and mechanical system and set it as FV analogy. Here we are using for voltage. V is for voltage. Here we are using the capital V for voltage and a small v for velocity. Alright. Now in the electrical system, till now we are discussing the series circuit. Now in the case of, if we take the parallel circuit, then we can develop the analogy for Fi analogy. So now in the case of parallel circuit, parallel circuit an externally applied current source I is feeding the three elements, that is R, L and C, with the parallel circuit. Here we have the three parallel circuit, so current will be divided. So I will be divided in IR, IL and IC. But because of this circuit is parallel circuit, the voltage should be equal. So we can say that in case of parallel circuit, the voltage V equals to VR, VL and VC. In the parallel circuit, voltage should be equal. So on applying the KCL, we can set it as I equals to IR plus IL plus IC. Here IR can be written as IR into VR plus IL should be written as 1 upon L 0 to T VL dt. Here VR and VL and VC should be equals to V, so we can write it as V. So here 1 upon L 0 to T into V dt plus of Q of 0. This is the case of inductor, so here we have the phi of 0 because inductor stored energy in the form of electromagnetic field. And for IC, we can use the similar term CdV upon dt and set it equation number 3. So now by using equation number 2 and 3, we can develop the analogy and set it as Fi analogy, where force is analogous to the current. Alright, so Fi analogy, in the Fi analogy, force is analogous to current and velocity is, here we have the velocity and here all the equation write it in the terms of voltage. So in this case the velocity is equals to voltage and also displacement is somewhere exactly analogous to flux. So X is equals to flux, and for mass, if we consider this equation mdv upon dt and cdv upon dt, then m should be analogous to c directly, and also for d, for damper is analogous to, if we consider this particular term 1 upon r into v and d into v, then d is analogous to 1 upon r. Similarly for spring, here K and here we have the 1 upon L term. So K is analogous to 1 upon L. So here we develop the analogy in between the electrical and mechanical system, and these two tables indicates how a circuit is analogous, how a electrical circuit is analogous to mechanical system, and if we take the FB analogy, then we will have to apply the KVL equation, or we have to connect all the elements in series, whereas in case of Fi analogy, all the elements, we are trying to connect all the elements in the parallel form and with the help of Fi analogy. Okay.